Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah, so it is a pleasure to introduce Krzysztof Ostrowski, a fourth-year PhD student from Cornell. He's Ken Birman's student, who was coincidentally my advisor too. So I'll let Krzysztof start off with his work on QuickSilver Scalable Multicast.
Thanks. Okay, so this talk will be mostly about QuickSilver Scalable Multicast. It is a scalable, reliable multicast engine we have built at Cornell. But I also want to talk a little bit about the context of this work, the general context, because this work is not a goal in itself, it's just a part of a larger piece. So the first part of the talk will be dedicated to the general vision that motivates my research. And this vision is to make a publish-subscribe paradigm into a real service-building component integration technology. We believe that the existing technologies, the client-server and peer-to-peer approaches, are insufficient. There's a whole group of applications that you could build that you cannot build with those approaches, and that peer-to-peer will enable. And the first step, of course, there are several steps towards that vision. It's a larger agenda, but the first step towards that is to show the feasibility, to build a multicast engine that can achieve high performance and scale in a number of dimensions at the same time. So during the remainder of my talk, I'll talk about some of our experiences building such engine, how it scales, how to make it scale, how to make it work with high performance, and in particular, how the fact that it runs on managed environment is significant. So like I mentioned, we believe that the existing technologies, client-server and peer-to-peer, are not sufficient, and that's because they offer disjoint sets of functionality, and developers have to choose among that. So for example, the client-server paradigm, you can build services that are interactive in the sense that clients can modify the state of the service, and you can have a large number of clients doing so concurrently in a reliable, consistent manner. On the other hand, this technology doesn't scale very well, and if it does, you have to use costly hardware and lots of infrastructure. Now, peer-to-peer allows you to build very scalable systems, but usually the flow of information is one way. In this sense, this approach is not very interactive. Also, those systems very rarely give you any end-to-end reliability guarantees. So we believe that with publish-subscribe, you could have it all. Of course, but publish-subscribe done right, meaning that it has such that has reliability properties, such that scales in a number of dimensions, such that has clean language and system embeddings. And so in particular, so why would you even bother about such combinations of features? I will point one example. There are services that we would like to be interactive and decentralized at the same time. So here's an example. Suppose that live.com were to feature something we're going to call a world composed of virtual rooms. In essence, it would be like a massively multiplayer game. But now, instead of Microsoft being the content provider, it would be users that would provide the content. So just like today, you can create web pages which are relatively static type of content. Now you could create virtual places that are three-dimensional locations. You could design the interior of such place. You could place a content in there. You could create hyperlinks from such places to other places, magical corridors of some sort. And then you could invite people there, and you could meet those people in 3 dimensions, talk to them, interact with them, just like you do in a game. Now, so obviously, this is the sort of content that is much more interactive, much more dynamic than just a static web page. Now, we also believe that in order for this to be practical, you need decentralization. If I create such a virtual place on my home machine, it is infeasible that this machine acts like a gaming server suddenly. I want to turn it off at some point. And it's not likely to have the capacity for this. Also for Microsoft, it wouldn't be feasible because there may be 200 million, perhaps, of your MSN subscribers now suddenly creating virtual places. And they may be doing things like streaming audio to each other, maybe projecting even movies to each other in a virtual conference room. So you don't want all of this to go to a central server at Microsoft. So you want those people who enter a virtual location to communicate directly with each other. Now, if you think of if you think of a virtual room as a service, so it has to be interactive and decentralized. And the publish subscribe is a perfect match for this. You can think of a room as a service itself, as a topic, publish subscribe topic. Now, as you enter or leave a room, you subscribe or unsubscribe. The state of the topic, how the place is designed inside, who is standing where, what did they say, is replicated among all the people in the topic, among all the subscribers. As you enter, you perform state transfer, you load the state of the topic. As you move around, you publish updates. And these updates are disseminated consistently in order to all the other subscribers. And exactly the same approach can be used in a lot of other applications. So publish subscribe topics could represent stocks in a trading system, documents that are collaboratively edited in some future version of Microsoft Office, perhaps. Sets of devices governed by a certain security policy, sets of services in the data center that have to jointly process a certain type of customer order. We know that the data center architects try to build data centers using publish subscribe approach exactly in this manner. So if you think from this perspective, we want to use publish subscribe topics in a very casual manner. There are something like files, like objects. So we really want to build like a new approach to programming that is topic-oriented. Topics are just yet another type of programming construct. And we could do that. We could embed publish subscribe into the programming language, just like you did it with language-integrated queries, just like it was done with Windows Communication Foundation, where web services were embedded. So even a person completely unfamiliar with building replicated services could create such services. And by this, I don't mean just a crude embedding of publish subscribe using Windows remoting, where you try to make everything look like an object and you try to provide complete transparency. I mean a real embedding where certain features of certain aspects of the fact that the publish subscribe topic is a distributed entity are actually visible to the programmer. Okay, here's another example of an embedding, this time a shell embedding. So through a shell extension, we provide a virtual hierarchy of folders. In those folders, you see files. Those files are actually topics. So for example, there could be a file that is a game. But there could be a file that is an actual location in a game. There could be a file that is a conference room. And instead of representing a content that just sits in a file system, this would be essentially content that you can walk into, you can join, you can interact with. And so when you right-click on such topic in our shell extension, you would see a list of actions. What those actions are would depend on the type of the topic. So whether it's a game, for example, you could walk into a game when it's an audio stream, you could record it perhaps or listen to it. So it would be determined by the time of the topic and the sorts of client software that you have installed on your local machine that you could use to access the topic. Now, when you click an action, then appropriate client component would be launched, and it would be made to subscribe to the topic. So the whole mechanism would be very similar to file extension handling. Yes?
So the example you have the topic is your music collection for today?
For example, maybe these are not perfect examples because they're mostly like content distribution style, but you could have a game here or something like that. You could have a conference or something of this sort. So this is a very crude example. You can imagine other types of shell embeddings. So instead of a folder hierarchy, you could have a virtual building which would have virtual corridors. In those corridors, you'd have doors. When you open the door, you can walk into a conference or you can walk into a game, stuff like that. And you could use one of the number of keys to open a door and give you different types of access. This would be like selecting an action here. Now, from a more technical point of view, topics would have types that represent the type of content that is being replicated, the types of updates that can be applied, the type of behaviors that are available or required, reliability, security aspects, and so on. And so applications would also be typed. So when you select a topic, the operating system would perform a type matching, find all the clients that are compatible with this sort of a topic that could be used to consume this topic, to access the topic. And that would be the way to compile the list of actions. Now, going further, a publish-subscribe engine of this sort would have to be an integral component of the operating system. Just like files from the file system can be consumed in different ways from the shell, from the application, we all want the same for the topics that are provided by the publish-subscribe engine. So you could use them as objects or some sort of a socket in application. You could use them from the shell, and you could use them from Visual Studio, just like web service. You could click on a topic, say, I want to implement a client stub that will be able to access this topic that I could later just customize with my specific functionality. Now, we need not just any publish-subscribe engine, but one that meets a number of requirements. So first, you want scalability. And here, especially this dimension of scalability, where you scale to thousands of such topics. So most existing systems don't really care about this dimension of scalability, and yet this is something that we would certainly need. Performance, so high throughput for multimedia streaming. On the other hand, low latency for gaming. And we believe that this paradigm could be used by data center architects. So if you want to justify using this whole software on their expensive platform, it has to use the full power of it. You need reliability guarantees. So even in the virtual room example, as you move around, you want to have total ordering. You want to have total, you want to have atomicity of distributing the updates. So even in this very crude example, strong properties would be required. You want all those embeddings to make it usable for anybody to actually bother to use this technology. And if we want this technology to be as successful as web services, to be some sort of web services number 2, we want interoperability standards so that we can perform collaborative development. Now, touch upon this point later.
So there are other pub subsystems out there, right? Like TIBCO.
I'm getting to that.
Oh, okay.
So there's a number of technologies that are PubSub in flavor, and none of them really provides all the features you want. So group communication provides very strong reliability, exactly the sort that we would need, but unfortunately those systems don't scale. There are existing PubSub systems. They hardly provide any sort of reliability, end-to-end reliability, and they don't scale in all of the important dimensions anyway. And they don't have as high performance as you would want. They're not appropriate for streaming scenarios. They're usually focused on singleton events, right? And there's this whole class of so-called reliable multicast protocols used for streaming. They sometimes offer simple form of reliability. They usually have very good performance, but they still don't scale in all of the important dimensions. Very few systems care to scale to thousands of topics. Most protocols actually don't provide any explicit support for multiple groups or topics. And the goal of the QuickSilver platform, the system I'm building, is to give you all of these features eventually, and we're getting there in 2 steps. So first step is to break this performance and scalability barrier, to prove that you can actually have simple form of reliability and very high performance and scale in all of the important dimensions at the same time. So this study is meant to give us confidence, establish credibility for this work. This is a finished system. QuickSilver 2, the system that is currently under construction, is focused primarily on very strong types of reliability. So here we'll provide a mechanism, a single platform, where you can have topics with a virtually synchronous property, with transactional property, with consensus-like semantics. In fact, what we'll provide is a simple domain-specific language. We can specify protocols as complicated as virtual synchrony in 20 to 30 rules in this language. And we will automatically translate this semantic description into an actual protocol. Yes?
What is this 30 rules?
I'm sorry?
I'm sorry, you mentioned something about some rules.
Yes, in the second version of QuickSilver that we are building right now, instead of giving a single protocol, we will give you the ability to describe your protocol, the semantics of your protocol, in a domain-specific rule-based language that we construct. And you will not have to worry about any aspects of scalability, only specify the semantics. And we will translate this description into a scalable hierarchical protocol.
So do you have an example of a protocol?
What is a protocol?
Virtual synchrony, transactions, all this will be supported. So for those examples, we know how to do that. And we believe that you can do it for a large class of protocols. If you can do it for those 3 examples that we focused on.
So would SRM be a protocol?
Oh yes, this is simple reliability. This is something that you already have in QSM, right? SRM gives you a simple acknowledgement-based type of reliability. So that is what we already have. So QSM, as I mentioned, it's acknowledgement-based reliability. It is written entirely in .NET, mostly in C#. We tested it on a platform of 200 cluster nodes with 100 megabit network and 1.3 gigahertz CPUs. In those ranges, we get throughputs basically as high as this network allows. And as we scale in those ranges, that up to 200 nodes and 8,000 groups, the performance decrease is only a few %. So we believe you could probably go higher. So now let me focus more on QSM itself. First on the scalability aspects. So how do you design a scalable protocol? So one of the fundamental design principles behind the whole QuickSilver platform is a separation of concerns. So the way we see it, publish-subscribe engine has three jobs to do. One is to disseminate data efficiently and worry about things like flow control, rate control, scalability. Another job is to ensure reliability properties. We consider this task as completely separate from the former. And here, of course, we're talking about things like loss recovery, ensuring atomicity, view synchrony, or whatever. And finally, the management of the entire structure, determining the hierarchy, choosing the right protocol to run in a particular place of the network, managing membership, detecting failures, and so on. So our platform is built with this distinction in mind. All the three jobs are performed sort of separately from each other. So let me talk about dissemination first. And I'll focus on the aspect of dissemination where we want to support thousands of topics, because the scaling to large numbers of subscribers is fairly well understood. We know that we have to, most of the time, apply some sort of a hierarchical approach, limit the number of neighbors that you talk to avoid things like NAC implosion and so on. But few systems focus on this other aspects of scalability. So what are the existing two approaches? There are systems that use IP multicast. Here, mostly, we just assign a separate IP multicast address to every topic, and we run a completely separate protocol for every topic. So those systems can scale to very large numbers of subscribers. But obviously, there's this linearly increasing overhead component. There's a per topic protocol stack, per topic control traffic on the network. So this is not the way to go. There's another approach. A representative of it is a spread system and other lightweight group approaches. Here we use proxies to relay messages to clients. In those systems, we can actually scale better with the number of topics. And there are some ways to amortize the overhead. For example, when a proxy has to relay messages in different topics to the same client, it can perform batching and save on some of the network overheads. But then you have proxies, and these proxies represent bottleneck. They sit on the control path. They have to relay all the messages. So those systems usually don't scale to very large numbers of subscribers or to very high data rates. And furthermore, those systems usually rely on filtering on receive. So if the overlap between topics is not very regular, you have lots of inefficiencies. So we ideally want to have an approach that combines. Yes?
Chris, since you work in this area, do you have a sense of, I mean, there have been people who have recently proposed using sort of PHP-based sort of frameworks or systems to do pub/sub.
Right. So those
do you have a sense of how well those would scale? I mean, people have.
I would classify this as the second approach, where you'll use proxies, right? Because that's essentially amounts to forwarding. So, well, yes, those systems scale to a large number of subscribers, but you still have those proxies. There's latency, there's bottlenecks, right? Plus, I think most of the systems really talk about a single topic, a single dissemination structure. So in this sense, they don't scale the number of topics either, right? At least they don't provide any specific support for this. So we're trying to build something that's sort of midway through, where you can scale in both dimensions. So what we do in QSM is we partition the entire network into regions. Those regions are defined in such a way that all nodes in the region have similar membership. And now, just to make it simpler, let's say that membership is identical. So region BC would be defined as all nodes that subscribe to topic B and C, but not A, right? And the topic A, for example, would span over 4 regions: A, AB, and C, and ABC. You could relax this definition, but let's just stick to it. So now we assign a separate IP multicast address to every region, and any node that sends messages will have a separate protocol stack component on a per region basis. And this protocol stack component will worry about things like flow control, rate control, reliability for that particular region. And when we send anything to a particular topic, the request to send gets split into sub-requests for each of the regions that the topic spans over. Now we see that we can still benefit from batching to some extent. When 2 topics map to the same region, those sub-requests will get transmitted, can be batched together, can be transmitted in a single packet. On the other hand, because you have similarity of membership, therefore every packet you send, it will be of interest to either all or almost all of the subscribers. So filtering is not much of a problem. Yes?
Good question. So is this aggregation, in other words, or?
Aggregation in what sense? I mean, that's a very general keyword.
So for anybody you're sending to some set of particular topics, you group them together, batch them together, and then send them out, right? Isn't that what you're saying?
Yes, if you send to multiple topics at once, then some of your traffic can get efficiently merged, aggregated. You can call it aggregation, yes.
Is this, I mean, you guys do this in an event-driven manner, or is this sort of multi-threaded?
Oh, I'll get to that later, yeah.
How does this scale, say, to as the number of users increase, the number of possible partitions, particle regions increase?
Yes, this obviously will, the performance will very much depend on the patterns of group overlap, right? How those topics overlap. So if you have singleton regions, it will not give you any sort of benefit. But then, I mean, nothing gets for free, so there's no free lunch. This is a way to give you performance benefits by exploiting any irregularities that are in the network. And in certain types of systems, you will have those regularities. Such as in a data center, for example, when similar hardware that is grouped into clusters is sometimes used to host different types of certain types of services, right? So
hoping that the application that you're considering will.
Well, I would say I'm hoping. I'm saying that if there is any irregularity, or if you as a system architect can arrange for there to exist an irregularity, we will be able to exploit it in a number of ways. This is just one way to do it.
We assume here the number of regions is not something. Number of disjoint regions formed by intersecting all the circles would not be that big.
You can say it assume, yes, but so this is a very rigid definition. We can define regions in a more relaxed manner, where membership wouldn't have to be identical. It could be similar, right? So you could arrange it for every region to be of size 20, for example, right? We can do that. And there you may use a little bit of filtering, but still have all these other benefits. So there's a trade-off, yes. Yeah.
So, not understanding something here. Is it the requirement that if I subscribe to A and everyone subscribes to A and B, okay, then is it required that I never get anything from B at all? Or is it okay if I receive some B along with my A?
Well, you don't want to receive from B if you don't subscribe to B. So we won't force you to do that.
Assumption, might it give you more?
No, not in a naive way, right? So we can relax in this assumption in the sense that the region may include you, and you may receive some stuff, but you just won't deliver it to the application. So that's the filtering part, right? Yeah. Okay. So to support this scheme that I just described, we have a membership service. So this is a standard component in any group communication package, but and there the purpose it serves is to provide a single source of agreed upon view of what is the membership of groups and how it changes subsequently, right? So we typically maintain a list of groups, and for each group a list of views. In our case, we also have to have an agreed upon view of how the system is partitioned. So we have regions and membership views of the regions, and we also maintain the mapping between the two. And the membership service delivers the relevant portion of this information to the interested nodes, so that nodes can rely on this upon as a common knowledge. Now let's focus on recovery. And here let's focus on this traditional dimension of scalability, scaling to very large systems. So the systems that scale to large sizes typically have to control node fan-out, the number of neighbors you talk to. And to this purpose, they usually create various types of hierarchical structures. So on the left, you see an example of acknowledgement tree of the sort used in RMTP protocol. Now, this is very nice if it's for a single topic. Now, if you have 1,000 of topics, it's not going to work. Because if the coordination of those trees or other structures used is not if creation of those trees is not coordinated in any way, you may still have a number of neighbors. You may still have 3 neighbors in one tree, 3 neighbors in another tree, and perhaps a few hundred neighbors in total. So to avoid this in QSM, we perform recovery in a hierarchical manner. So you have multiple layers of protocols running at different levels. And what those levels are. I already explained that groups map to regions. So you can topics map to regions. You can sort of think that topic includes a number of regions. For reasons I'm going to explain later, we also partition regions into partitions, right? And the partitions contain individual nodes. So you have 3 levels: topics to regions, regions to partitions, and partitions to nodes. And now we have 3 levels of recovery protocols. So in every partition, nodes in the partition run a recovery protocol. In every region, all partitions in the region, in turn, run a recovery protocol. So that's a higher level protocol. And finally, for every topic, regions in the topic run a recovery protocol. Now, where the saving comes from, the protocol that runs in the region runs for the benefit of all topics simultaneously. Or I say the whole group of protocols in the region. So if you have 10 topics overlapping on a given region, still a single protocol will perform the loss recovery for all those topics simultaneously. Here's how this works. This picture shows a single region of 3 partitions. So these yellow disks are the partitions. In every partition, nodes run a token ring protocol. The token in this ring is carrying information such as who received what and other such. The nodes can compare the tokens of the ring with their own state, and this way they arrange for and push and pull forwarding of packets between them. Apart from local recovery, they also aggregate information about this entire partition. Examples of such aggregate would be what packets have been received by everybody in the partition, what packets are missed by everybody in the partition, and so on. Now, this aggregate is collected by the partition leader. Now, partition leaders only deal with such aggregates now. They form another token ring. They perform a regional recovery. They can arrange for forwarding between partitions. And again, they calculate aggregate information about the entire region. And this aggregate is collected by the region leader, and so it continues hierarchically.
Why use token rings?
I'm sorry?
Why use token rings as in why not use something?
We can use anything else. So yes, I'll talk about generalizations. Actually, this is my second slide. So
this is going to add delay, right? Such an architecture is going to add more delay in how much time it takes for any of this protocol to complete. Right? So have you quantified that? How much delay is this going to have?
I think it will be explained in the later slides. But yes, we are not tied to token ring. There's nothing specific about the token ring. It's just something that we chose.
This is a hierarchical technique. It's kind of a virtual hierarchy.
Yes, the point is the hierarchy is the point, sort of. Not the fact that we are using token ring. It's just something that we use there. So what are the key insights here? First insight was to exploit regularities wherever they might be to get you higher performance. And like we discussed, it may not always work, but it will give you savings wherever you can arrange for such regularities to exist, or wherever we can trade. Perhaps we can trade filtering to generate such regularities, right? Another key idea was to perform the task of recovery in this hierarchical manner, where you take a number of protocols at different levels and they get composed. Yes.
Maybe I missed it, but how do you actually detect these regularities or these overlaps?
Let's take it offline because I think it's a longer discussion. So first you can reuse protocols, right? Like as you saw that a protocol that runs in a region can work for the benefit of multiple topics. And secondly, the whole task gets hierarchically decomposed, which gives us the ability to locally optimize. And I will explain it on the later slide. So here's the general philosophy of this protocol design. So the green disk represents the region again, and the pink disks are the partitions, and the yellow boxes are the nodes. So now we talked that some nodes perform certain specific functions, such as being a leader of a partition or a leader or a region. Well, another way we can think about this is that every entity, every node, any partition, every region, and so on, has an agent that acts on behalf of it, right? So the blue agents, and those agents live inside of the nodes. Nodes are now thought of as containers for agents. So blue agents perform local recovery. They could run, for example, a token ring protocol, right? They could perform local recovery as well as collect aggregate state for the pink thing, right? Which in this case would be a partition. This aggregate is given to orange agent, right? Now orange agents only deal with such aggregate. So an agent that represents a certain entity will only deal with the sort of state that describes this entity, nothing below that. So the orange agent will never deal with anything that pertains to any particular node. Now orange agents talk to each other. They calculate aggregate about the entire region. This aggregate goes to a green agent, and so on, right? Now what's the key of this approach here? Every interconnected group of agents could run a completely different protocol, right? They could run token ring. They can run a tree. In fact, they can run a protocol with a slightly higher reliability guarantee. Maybe this pink thing is a group of servers that are some sort of a state machine, and they actually have to have atomicity, view synchrony, ordering, and everything else, right? It is possible in our approach, as long as you communicate with agents below you and above you in the agent stack using a standard protocol, right? You can do what you want in your layer. So if you instead of regions and partitions, you can think of the entire internet being composed into organizations, data centers. In those data centers, LANs, and so on, so on. There's a hierarchy of this, right? So for nodes that are in different data centers, it doesn't matter that they run the same protocol. So we can tune those local protocols to adjust them to local topology, node capacities, availability of IP multicast, and so on, right? And this way we can optimize. So this approach is our way to building the fastest system out there. Instead of insisting that we have this golden solution that works in every possible case, we're going to do the other way around. We provide the infrastructure that is very flexible, that allows you to tweak any part of it. Any local protocol, any protocol running at a higher level, independently of anything else, right? Precisely the same approach can be applied to dissemination. We can define a forwarding policy that works between data centers. We can define forwarding policy or other dissemination policy for every data center. And all these policies can be combined together to form a single structure for dissemination. OK, now, just to wrap it up, let me show you what's the outcome of all this. Here, we test on a cluster of 200 nodes, as I mentioned. A single sender or two senders send 1 kilobyte messages to a large number of subscribers. So there's only a single published subscribe topic. And we vary the number of subscribers, and we measure the throughput. So as you see, with two senders, we can get very close to what this network can deliver. It's a 100 megabit network. And throughout the range, our performance drops by just a few %. So if you had larger hardware, quite possibly you could scale to several hundred to maybe even 1,000 nodes with this approach. And the latencies are acceptable. It's 10 to 25 milliseconds. It's not great, but it's OK. Yes?
What's the topology here? How are these?
This is a single cluster with a number of switches there. It's all local area network. It's a single multicast domain.
So no loss, nothing, absolutely nothing.
Oh, yes, there is loss, sure. But it's not very frequent. Right? Loss doesn't, we don't care about loss in the network. In these scenarios, like in data centers, loss mostly occurs from dropping packets by the nodes themselves because they're too busy to process all this, right? So this, I'm sorry?
Given that you were sending 1 kilobit messages, was there really any losses? Or?
Sure. The loss was, okay, I don't have numbers for this particular picture, but loss happens, I don't know, maybe 0.1% or something like that, not a significant one. But I'll talk about the experiments where you introduce the loss. That's the next picture. So, well, okay, going to this example. So here we introduce artificial loss. It's precisely the same setting. So one node is a bad guy. We perturb it on purpose. Every second we introduce a 10 millisecond slot where we drop every type of packets that arrives. So it is artificial 1% bursty loss. We drop packets in bursts. That's what happens in real data centers. The actual loss that we're dealing here is actually like 4 to 5% because because of the artificial 1% loss, we have to perform recovery. Now the fact that you have recovery starts to interfere with the regular multicast, so we end up having 4 to 5% loss. And here we again have the throughput curve. So it doesn't decrease that much. Why it falls here is because we have this artificial size of a sliding window on the sender. As the system grows, the latency for cleanup, for acknowledgement is growing. And at some point, we're starting to hit this upper threshold that we have artificially set, 100,000 packets of the sliding window. If we hit this threshold, the sender pauses briefly and only recovers when the sliding window shrinks. So it is sort of like a flow control. But within this range, it goes pretty well. And if we increase this threshold, we could go further without that much of a performance decrease at the cost of slightly bigger memory consumption. In the left case, we do a similar thing, only that instead of introducing artificial loss, we artificially freeze up the node. So every 5 seconds, the node pauses for half a second. It goes into infinite for loop, or not infinite, half a second for loop. And because our system is single-threaded, as I'll talk about it later, this pretty much stops the flow of time. So we're stealing 10% of the time from the node, and that's the result. So yes, the performance gets worse, but doesn't collapse. Yes?
So you mentioned that you had 200 nodes, right? And they were all in the single multicast domain? Mm-hmm. So they were all on the same subnet?
Yes.
Okay. So did you consider simply using subnet broadcast? What would have been the performance?
Subnet broadcast?
Yeah.
I'm not familiar with it, so.
Yeah.
No, just send out a broadcast packet, IP broadcast.
Yeah. Why not do that?
That's like having a single region for everybody?
Sure.
That's a lot of filtering overhead. This is what we're trying to avoid, right?
Yeah, but you probably introduced extra network overhead, right? Because if you weren't doing broadcast, that means the same message appeared on the network multiple times, and depending on how your topology was structured.
Okay, yes, let's talk about it later because that's a longer discussion. But yes, this boils down to the different patterns of overlap and what's the consequence of having that. So let's talk about it later. Let me just finish those performance numbers here. So in the upper left corner, it says artificial test for testing how much performance penalty you get by just having multiple topics. So here we have a single sender, a large number of subscribers. All of these subscribers, 100 of them, subscribe to exactly the same topics. And we vary the number of those topics, right? So these topics precisely overlap on the same group of subscribers. And we test the performance. Well, we can get to a few thousand with a few percent performance penalty. And the penalty is mostly memory related. Yes?
Sorry, I'm still having trouble with this. Why is filtering overhead a concern?
Let's take it offline. I don't think there's point of going into this discussion right at this second. In the upper right corner, we vary the throughput, and we measure the CPU overhead on the sender and the receiver. So this shows that the protocol is fairly economical, right? On the 1.3 gigahertz CPUs, you can send or receive a few megabytes per second and have 3 CPU cycles. Okay. In the last part of my talk, I'd like to focus on delivering high performance. So to get really high performance, we have to stress the system, and then it turns out that lots of resource limitation occurs. And in particular, the fact that you are running in a managed environment starts to matter. Let me show it in a simple example. So you see the familiar picture on the upper left corner as the throughput decreases with the number of nodes. Now, why would the throughput decrease, right? Let's look at the CPU graph. We know that the loss is fairly small. It's not significant enough to justify this throughput decrease. So, and we know that the receivers have plenty of free CPU cycles and the sender is busy. So the reason for the decrease in performance is on the sender. As we profile the system, we realize indeed the time that QSM spends in its code, it's decreasing, whereas the time spent in the CLR is increasing.
Were those 1,000-byte messages?
Yes.
So you're delivering 8 million bytes per second at 80% of looking at throughput versus
Yeah.
processor overload
Mm-hmm.
on 100 megabit NIC?
Mm-hmm.
Can't do that.
Why not? 100 megabit NIC you could do theoretically, but
You can do 10, yes, it's part of it. But it keeps slipping digits going between 100 megabit and gigabit.
sure. Yeah. So we realized that the decrease in performance is mostly due to the increase in CLR activity. Now, as we dig deeper, we realize that actually the cost to allocate memory is increasing linearly with the system size. Now, remember that our throughput is actually decreasing. Why would that be? Same for garbage collection. So it's not like we're allocating more memory or doing it more frequently. But the memory used on the sender is increasing. And that is because it takes, there's more packets that have not been acknowledged. And that is because the time to acknowledge a packet is increasing. And that is because, obviously, the time to circulate the tokens is increasing, right? This is what we could have expected. But who would have thought that this slight increase in the latency and the resulting 10 megabytes of difference in memory overhead is going to cause so much performance degradation. So we found the link, the mechanism that links latency of the state aggregation in a reliable multicast protocol to throughput directly through increase of the memory overhead and garbage collection and memory allocation activity. A much stronger sort of a link that we would have thought there would be. So okay, latency is a problem. So we can redesign our protocol to reduce the latency. Is there any other dirty quick fix that we could apply? Let's increase the intensity of the state aggregation. So now instead of releasing a token once per second to collect the state, let's increase it a number of times per second. Would that help? Well, as you see in the upper left corner, as we increase the token rates, at some point the gains are negligible. At the point when you have more than one token in the ring, it doesn't really matter. Okay, so intensity of this is not the answer. It's still latency is the only solution. Well, could it be about the amount of state that you aggregate? So our tokens carry structures that are series of numeric ranges. For example, packets from 1 to 10,000 and 10,005 to 20,000 and so on can be cleaned up, right? As you vary the maximum number of such intervals that you can include in the tokens, you vary the amount of feedback. And you vary the ability of the system to skip over gaps in the message sequence, right? So let's increase this linearly with the system size. Will this help us to reduce all these other negative effects? And that's what you see on the upper right corner here. The pink line is the regular case, and the green line is this modified scenario. Well, indeed, memory consumption decreases quite noticeably, although still it's not flat. But then the throughput also decreases. So what's the outcome of all this? Yes, we could have reduced memory overhead, but then the protocol became slightly more complex, not that much more complex, but that was enough to actually reduce our performance. We had slightly more work to do. So this is, again, not a solution. In fact, what happens here, occasionally the system becomes slightly unstable because the sender is very fast to resume a multicast. Remember I told you about this window, the sliding window that is used for flow control? Now, because cleanup happens faster on the sender is more eager to start multicasting again. But the receivers, they have to deliver packets in a FIFO order. They cannot just clean up any random stuff that has been delivered everywhere, right? So on the receivers, memory consumption is bigger. And as a result, their ability to accept incoming packets is reduced. And we will occasionally run into this bursty activity. So what's the outcome of all this? In a managed environment, memory is surprisingly costly. And that teaches us that we should really reduce buffering as much as possible, possibly completely just eliminate buffering from our system. And we shouldn't also use caching without limits. Sometimes it's just better to throw things away instead of caching them for the purpose of recovery. And that is a lesson that we have applied in our system. Another lesson is that latency of state aggregation turns out to be surprisingly important because it is connected to throughput by all these memory overheads. And by the way, I just showed you a simple example, but pretty much in every single experiment that we run, in all these different scenarios, memory turns out to be this link that connects latency to throughput. And memory turns out to be the real factor that always degrades performance in this way or another, either on server or on the receiver, always latency. So, OK, we can design a different protocol. And this is what we do in QuickSilver 2. To now, instead of having just 3 layers with rings, we can have an arbitrarily high hierarchy. And then we can keep the latencies, but possibly it's still under construction. But possibly we could keep latencies somehow growing logarithmically instead of linearly, right? As we can do it with the system with fixed number of layers. But as I'm going to show in a second, most likely we will still have some problems, maybe not as serious, but still some, because latency in the protocol is not the only source of latency. So here's you like it? So OK, so what forces are at play in our system? This is the series of interconnected phenomena that mutually reinforce one another. OK, so there are some sources of latency. Protocol, for example. There are others. This leads to increase in buffering. So the packets sit in the protocol stack on the sender, right? Either because they're waiting for transmission, or because the sliding time window hasn't been shrinked, or because they have not been acknowledged, other purposes. And there's caching overhead. On the receivers, these packets have to wait until it's their time to get delivered. This causes memory overhead. You've seen that. And this leads to increased activity of the garbage collector and more memory overheads. And this leads to scheduling delays. What I mean by this is that where we're doing some work now we suddenly get preempted by the garbage collector. So this rest of the work gets delayed. Or we're doing some work and we have to allocate this memory, and suddenly it takes more time than we would want it to take, right? So our work gets delayed in this way or another. And this turns out to affect latency. It wouldn't matter if it's just a single node, but if you have to do things like aggregate state over a large number of receivers, these latencies add up, and they can become significant, as they indeed are in our protocol. If memory overhead on the receivers grows, we can immediately see impact on throughput. And there are other loops in this picture. This is just a subset of all the different forces we could have portrayed. If the latency increases, the system may act upon stale information. What I mean by this? Let's suppose that node A sends a request to node B to forward the packet. And by the way, these are all real phenomena that we happen to run into in our system. It may take time for B to look at this request because, for example, it may sit in buffers on A, waiting to be transmitted. Then it may sit in queues on B, waiting to be looked at. Now, if it takes some time for B to look at this request, A may actually recover this packet from elsewhere. Now, if B now acts upon stale information and still forwards, it's going to do useless work, redundant work. And this redundant work is just as disruptive as the garbage collector. So it causes delays and so on. And other sources, random scheduling. What I mean by this, scheduling that doesn't pay any attention to the relative priorities of different types of events. So important work gets more delayed. You end up with a priority inversion. This basically you can look at it as delays. Because control packets, such as the token, are the most important factor that affects latency. So if the control packets are not, if processing such packets is not prioritized over other types of packets, this translates into the bigger delay overall. Now, preemption is another problem. Most tasks in our system, actually every sort of activity in our system, is very short and absolutely terminating. So any preemption is just pure overhead. Also, when you have to synchronize things, it's just useless. Even activity has to take 5 microseconds, and then occasionally you'll have to wait 1 millisecond until you get that lock. It's again pure overhead. And finally, there are weird cases of starvation in our system, or you can call it like extreme case of priority inversion. So to combat problems caused by random scheduling, we prioritize certain types of processing over other types of processing. For example, we are more likely to process I/O faster and a little bit lazy to inform the application that the request has been acknowledged, for example, right? Application doesn't seem that important at this point because it's not on a critical path. But then what happens is that we don't call the application to inform it that the request has been acknowledged. So the application still references the object. Because it references the object, the garbage collector cannot recycle the object. So what you end up with is that if you freeze the system and look at the managed heap, you will find that the number of objects on the heap is actually a few times higher than what you would expect, than the number of requests that have not been acknowledged. So this weird priority inversion blows up your memory consumption by a certain factor, and it decreases your performance, causes latency, and so on. Now, how could we combat those problems? So one thing we do is we introduce flow control to the OS. That's pretty much straightforward. So we limit the number of data that is being transmitted, the number of requests to send, and so on and so on. And we combine it with a pool-based protocol stack. So our entire protocol stack does almost no buffering at all. Every packet is, control packet, data packet, is created just in time for transmission. For once, it reduces buffering, almost eliminates buffering. For two, it causes our packets to be more fresh, right? Because at the time they are transmitted, they are created. So they represent the information from this particular moment, not information from some while ago. And this was pretty important to this optimization to avoid cases like endless forwarding, because we forward. We could have stopped forwarding because we could have been told that this other node actually has that data, but we didn't get told because all this control traffic got delayed, right? And now with more freshness in the system, we can avoid those problems. And finally, we reduce caching by applying collaborative caching. So in our system, actually, the overhead of caching is linearly decreasing with the system size. And just a brief comment on what I really meant by pool protocol stack. So every socket is a root of a tree of protocol components. Those protocol components act as a feed or a sink, depending on how you look at them. So a feed is somebody who has data and wants to send it. Sink is somebody who can send that data downstream. Now, instead of pushing data to the sink and letting it buffer, just like it is the case for most push protocol stacks, a feed only registers the intent to send, and the sink maintains a list of feeds. And the sink is driven by concurrency controller, rate controller, perhaps window size, and so on. So sink won't send immediately. Sink will wait until it is an appropriate time to send. If the sink thinks it's a good time, it will register with the downstream sink. Eventually, somebody will register with the socket. The socket will pull information from the protocol stack, and it will keep pulling in a round-robin fashion until it decides it's not a good time to send anymore. We have no more data. We now register. We have data again. We re-register, and so on. Now, what we mean by cooperative caching, every message that is received gets cached. Every message gets cached by only k nodes, where k is typically five in our system. This seems to be a good trade-off. So if you have this responsibility to cache is distributed among partitions. That's why we decompose the regions into partitions. So in a region of 15 nodes, you will have 3 partitions, typically. And each of them will cache 1/3 of the data stream. In a bigger system, it will cache proportionally smaller fraction of the data stream. And this turns out to be a much better idea. If we increase the number of the amount of caching, if we reduce the number of partitions, performance drastically drops. In fact, you really cannot run our system with a single partition with 200 nodes because it just blows up.
Who does the housekeeping about
Oh, the global membership service determines how to do that. Here's another set of optimizations. So we completely eliminated all multi-threading in our system. I'll explain this later. So we took care of preemption and synchronization overhead. So of course we can still be preempted by the application threads or other sources, but at least we don't preempt ourselves. We also eliminated random scheduling. So our implementation is completely single-threaded, event-driven. And so there are different types of events: incoming I/O, outgoing I/O, control packets, data packets, time-based events, and so on. Each of these types of events has assigned a quanta, it has assigned priorities, and we have our own scheduler that determines in which order those different types of events have to be processed. Now, so here's, maybe this is too complicated a picture, but what you see essentially is that we use a Windows completion port. Here we call it an I/O queue. All sockets, all types of I/O are connected bound to this completion port. So whenever we receive a packet or as a transmission completes, an appropriate record is placed on this I/O queue in the system. And we don't get a callback. Instead, it just stays there, and we will pull the I/O queue at an appropriate time. We also have an alarm queue for timer-based events. This is implemented as a splay tree in our program. And there's also a non-blocking queue for application down calls. It is non-blocking because application can be multi-threaded. We are single-threaded, so there needs to be some mechanism for those different types of the application, single-threaded and multi-threaded one, to communicate. So we have those three queues which we can pull, and we pull them one after another, and we process events from those queues in batches. And we have our own time sharing policy. So a cycle typically starts by pulling the I/O queue and reading all the events and queued I/O related events from that queue. Just briefly pre-processing them to determine what type of an operation it is. Is it an incoming control packet or perhaps outgoing data packet and so on? Placing those events in the appropriate priority queues. And just we keep going until we drain the completion port. If we found the data on a certain socket, sometimes we will drain the socket synchronously to make sure that there's nothing there left. When we're done with this is the red phase. We start processing those I/O events, actually processing them in the order of decreasing priority. Now, eventually, our I/O quanta will expire. Then we'll start processing timer-based events. Then the timer quanta will expire. We'll then process all application requests from the non-blocking queue, and we'll continue in the same fashion. And as I mentioned, our I/O is processed in the order of decreasing priorities. For example, we prioritized control traffic over data. It turns out to be really essential to get a good performance, because it's essential for these control packets to get through very fast, to remove those problems in the network. Otherwise, we could just keep sending, it will eventually blow up. Also, we prioritize the incoming traffic over the outgoing traffic because obviously we want to avoid packet loss. Okay, so these are just some of the mechanisms that we have applied in our system. And to conclude, I would like to point to certain areas where we believe improvements could be made in the .NET framework. Certain mechanisms that are really so general that they could, having a single implementation of those mechanisms, efficient one, could benefit many systems like ours. So first, we could have sockets that have pull interface, that have rate control and concurrency control built into them, that have priorities built into them. So you can prioritize communication channels. Faster serialization, we had to implement our own mode of serialization that uses the scatter-gather I/O efficiently. Also, as we realized in our system, multi-threading is totally useless. So we had to implement ourselves a purely single threaded event-driven approach. And we actually had to resort to 6,000 lines of C++ code for this because we couldn't have implemented it in C#. So we believe that this should really be supported by the .NET framework. The ability to write your application in a purely single threaded event-driven manner. So we would like to have the support for defining different types of events, assigning priorities to them, and defining quanta, just like it is in QSM. Also, there should be a support for a smooth cooperation between a multi-threaded and a single-threaded part of the application. In QSM, we have multi-threaded application and a single-threaded QSM. To make them communicate somehow, we had to use a non-blocking data structure. But even that wasn't enough. Sometimes we have to do hacks like posting a fake I/O event on the completion port, so that in case the QSM is in a blocking call, it will wake up. So we shouldn't be forced to do such hacks. It should be really supported. And marshalling, I believe, is not the answer, because it introduces just too much overhead. And finally, a more friendly garbage collector would be helpful with lower overheads and perhaps customized buffer management for different types of objects. And garbage collector that is, if we support event-driven scheduling, event-driven model, the garbage collector should be part of it. So it shouldn't preempt the entire system, just like it is in QSM. So to conclude, publish-subscribe could be really powerful. It could allow us to build the sorts of applications that we cannot build today. A different perspective on web browsing. Instead of static web content, we could have this interactive virtual realities. Different perspective on the operating system interface. Instead of a box with files, it could be more like a gaming console, where the content you see is really live distributed content, not just local content. And the sort of programming programming approach that allows a person unexperienced in distributed programming to create replicated services. I think this would be the way to go. And the work on QSM is a feasibility study. It shows that it can be done. So we know that performance and scalability, well, doesn't seem to be a bottleneck. Obviously, we could have done much more with our system, but so far, it seems like it's very promising. So this gives us confidence to build the rest of the system, to add stronger reliability properties, to add language embeddings, and we believe that it could be a successful approach. And that would conclude my talk, and thank you. I would like to take some questions. Yes?
Well, it seems that everything you built in this whole, your whole model is based, and your testing was done within a data center with less than a millisecond of latency. You had a nice network.
Right.
The real world doesn't work in that environment.
Sure.
What happens when you're talking about 20 milliseconds, 60 milliseconds, 250 milliseconds worth of latency between different components? It seems like latency was definitely one of the things that drove your system into the ground, and how are you going to compensate for that?
Well, now that we know about it, we know what type of protocol structures to look for. So I briefly touched upon this. Let me get to that slide. Let me just explain. Well, just like QSM is composed of those 3 layers, I mentioned that we could have multiple layers. And this is precisely what we do in QS2. So, okay, latency will be bigger. So having logarithmically growing latencies due to having a hierarchy of arbitrary size would be one response. You probably wouldn't get those sort of performance numbers in any sort of wide area setting, obviously, because latencies would be just too large. Perhaps controlling those memory overheads somehow, I don't know.
Do you have any simulation results in that scale, in the infinite-wide scale, or even larger data centers? Do you have any results in that?
We couldn't quite simulate this. I was trying to, but it's just too much of. I mean, it's too much of a complexity to try and rewrite this thing in NS2 or NS other systems like this. So we're looking for ways to either simulate it or run it on virtual machines. But one problem here is that, as the second part of my talk shows, it's not just about the network-related phenomena. It's actually more about the system-related phenomena, what happens on a given node. So if you virtualize it, you lose all of that. So your research suddenly becomes research on some completely different topic, right? So that's one real problem with this. Even we tried to run a number of instances of QSM on a single node. We can do that, but it's just a completely different category of experiment, right? You have a very busy application that has to trade time with another very busy application. They're going to compete, and so.
So how are you going to evaluate the system? You really need to show the correctness of your system. You need to evaluate it on a much larger system, either the internet scale or in larger data centers.
So we're looking. Well, the plan is try to find somebody who has access to a large data center who would help us to test it. Another approach is, well, I'm building this second version of QuickSilver now. And in that version, obviously, we won't be bound to IP multicast anymore. We can do those experiments in larger settings. Try to design a better dissemination protocol. Maybe that will help.
So I have another question. So your entire system depends a lot on this regions of overlap, right? That is, there will be significant overlap between different topics and different members. Have you done a study on how often it will be the case that you would get these overlapping regions?
There's not much data out there. That's the problem. We're hoping to get data from a specific data center, but it's just not the sort of data, the sort of traces that we would get available just like that. It's partly due to the fact that people don't really use PubSub on a large scale right now. So it's sort of a chicken and egg problem. You need people to start using it in order for you to get the real data, the real traffic patterns, and then to change your system to match those. So we are hoping that at least this work will help us to get this process started somehow. Of course, we can keep improving it until we get satisfactory results. Sure.
Explain a bit more what you mean by wanting a poll model for socket in .NET. I mean, are you actually asking to? Because I mean, most network protocols like TCP are inherently push.
Right.
So are you actually asking for the network transfer not to occur until someone asks for the data to come?
Right. So we had to design this mechanism, build this into this C++ part of the system, a mechanism where the whole rate control and flow control and the actual physical I/O are combined, right? So that you don't have to push data, right? You can just register an intent, and when a good time for sending comes, the data will be pulled from the whole protocol stack. So in order to do that, we can either hack it ourselves, right, or just have it in the.
I understand what you're doing.
I want to avoid the overheads of buffering as much as possible. This is the way to go.
But doesn't that mean you're just buffering on the sender?
No, this is on the sender. The pull protocol stack is on the sender. The sender doesn't generate data and place it into buffers that in different places of the protocol stack, but only the elements of the protocol stack register the intent to send. And so you have this tree of components that are registered mutually with one another. And at the root of this tree, you have the socket. And when you determine it's a good time to send, because all those rate controllers, flow controllers tell you that it's a good time, the socket will pull data from this tree in a recursive manner, right? So they'll keep pulling. You'll never have to buffer this data. You can still buffer a little bit just to avoid some overheads of going through the.
So this is all internal to a single process on machine. I guess I'm still not following the model here.
Well, it could be internal a single process. I mean, mostly use a socket in a single process, right? So a socket is typically a
you're not talking about pulling across the network.
Oh, no. Pulling across a single machine. Right. Yeah.